All right. So last time we have stopped at bisection. Okay. So now we are going to discuss the second method in chapter 1, which is the Newton-Raphson method. Okay. So you only have three methods in this chapter. So Newton-Raphson, I think the simplest one, the easiest one. Okay, compared to the other two. Right. So in Newton-Raphson method, okay, it is categorized under open method. Okay. So before this, you have bisection. That one is called the bracketing. Okay, bracketing method, because in order to start the bisection, you need to have the initial interval. But for the Newton-Raphson method, you don't really need to have the interval left and right, but somehow you need only one, okay, one initial guess, only one value, okay, that you put as assumption at the first place. It is your uh, um, approximation to your roots, okay, for the first iteration. Okay, so you only need one value, which denote as x naught here in your lecture notes. Okay, that is the initial guess for the root. All right, so before we go to the algorithm, okay, let me brief you the idea behind the Newton-Raphson method here, okay, compared to the bisection. Okay, so let us have simple diagram. Okay. um, okay. Okay, so before this, in bisection, okay, in bisection, we have something like this. Okay, so this is your A, for example, okay, and this is your B, okay, and the approximation is just by using the midpoint formula. So your C is just B A plus B over 2. This is in the bisection. You divide into 2. So it's somewhere here. So maybe for this type of graph, so maybe for the first time you already get your roots. Okay. But in different case, maybe I can do something like this. Okay, so maybe if we have a picture like this is A and B. So for the first time in the bisection, your C is here, but your actual root is marked by the X. Okay, but now in the Newton-Raphson, okay, in the Newton-Raphson, the same graph. Okay, so let's say this is your A, okay, your left limit, and somewhere here is your B. All right. So as I've mentioned just now, in Newton, you don't really need to have the A and B. Okay, you only need to have one value. Okay, so you either choose A, okay, at the left, or you choose B to be your x naught. Okay, so let's say I'm taking the B here. So at this point here, the coordinate at that point, so we can write as B, and the corresponding F is of course FB lah. Okay, so now in the calculation of Newton-Raphson, okay, we start with the x naught. So I'm assuming this point P here is my xi, okay, because we have the iteration. So xi, okay. So it means that at the BFB is also denoted as xi fxi. Okay, meaning that somewhere here at the y-axis, so this is your fxi. So now I can, okay, discard that one. Okay, so now the idea of Newton-Raphson is actually the approximation, okay, of our root by constructing a tangent, okay, a tangent line, okay, tangent at the point B here. So if you draw a tangent line, okay, tangent line, It's a line where if you compute the gradient at that point, it is 0. Okay, tangent. So have your ruler. Okay, so I put somewhere here. So this is supposed to be a straight line, my line. Okay, so that tangent line. Okay, so now if we form a triangle, okay, from the point xi, fxi, so see what do we have? So we have that triangle, which is actually a right triangle. Okay, so if we put the theta, so we have like that. And the point here, the intersection of the red line with the x-axis is denoted as your xi plus 1, because in the iteration, okay, in the calculation, you start with the xi, so the next value would be the xi plus 1. Okay, so your actual root, okay, where is your actual root? Okay, your actual root is the uh, blue curve intersect with the x-axis. Okay, so you see your actual is over here. Okay, but for the first time, your approximation is here. Okay, so this is the approximation to your roots. Okay, so you can see compared to the bisection, in the bisection, for the first time, your C is somewhere here. That is your approximation to your root, which is far from your actual roots. Okay, so by doing the Newton-Raphson, you construct a tangent line, so your approximation is actually closer to the actual roots. Okay, so that's why, okay, based on this explanation, okay, we can conclude that Newton-Raphson is supposed to be converged faster, okay, faster compared to bisection method, okay, because of this concept, because of tangent line. Okay, so that's the explanation. Okay, if someone asks you why tangent works faster compared to the bisection, okay, so in terms of graphical, okay, in terms of diagram, this is how you justify. Okay, so you can imagine for the second time you construct another, so for the second time you will start here, this point here. So if you construct another tangent, so you will have that triangle, so you will see you are getting closer to the actual roots. Okay, so that's the brief idea on the Newton-Raphson. Okay, so now let us see how do we come out with the formula. Okay, the derivation of the formula. So I'm going to, okay, okay, just concentrate on the triangle. Okay, so if you look at the triangle, if I take out, or if we write tangent theta, okay, what do we have? Tangent theta by looking at the triangle only. Okay, very famous formula, Pythagoras. Okay, so tangent is opposite over adjacent. Okay, so you can see the length of the opposite, okay, here, okay, the opposite length is fxi. Agree? Well, it is actually fxi minus 0. Okay, because the length here is fxi minus 0. Okay, so we can write as fxi only. Over the adjacent is, okay, so you can see from the diagram, the length is xi minus xi plus 1. Correct. Okay, so if I put the 0 over there. Okay, so now you can see at the right hand side here, this is actually the how you write mathematically the definition of the gradient. Okay, you have learned before about the derivative, I think, during your matriculation, as well as when you was in Form 4, I think. Okay, differentiation. This is actually how you write the derivative. Okay, it's just that maybe last time your notation is y, maybe. Okay, or you have the delta. Okay, so that is actually the derivative, which is the f prime. Okay, So the rest is just manipulate the expression. So if we can see this expression and this expression, okay, the only value that you don't know is xi plus 1. Okay, the xi is actually your initial guess, are supposed to be known by the problem. Okay, or you can take from the left or right limit. So xi is known. Okay, fxi, how do you get the fxi? So basically the evaluation based on the given function fx, you are supposed to know your fx. Okay, otherwise you don't know what you want to solve. Okay, so fx is given. So for any value of x, okay, xi here, you can obtain your f. So the only value or the only term that you don't know is xi plus 1. So if we isolate xi plus 1, then we have the Newton-Raphson formula. Okay, so you have xi minus fxi, so it's supposed to be I here, over f prime xi. So this is the Newton-Raphson formula. Okay, that's how you come up with the Newton-Raphson formula. Okay, so this is just for um, knowledge to you, so that you don't simply memorize the formula without knowing, okay, what is the justification or how do you derive the formula that you have in the Newton-Raphson method. Okay, how you suddenly come out with the derivative in the formula. Okay, why in the bisection you don't have any derivative? Okay, in the Newton-Raphson you have derivative because the basic idea is the tangent. Tangent very much related to the derivative. Okay, so that's the explanation, or how do we come up with the Newton-Raphson formula. Okay, okay, so now go to the algorithm. All right, first, of course, we need to have the function fx. And then we need to determine the f prime, because in the formula we have the derivative. So f prime is the derivative of f. Okay, a little bit of differentiation involved here. So you should know basic um, techniques, okay, of differentiation, the product rule, the quotient rule. Okay, so in this course we are not really, the intention is not really on the derivative. We don't our intention is not on the derivative. It means that in the problem it is something that I think I can say simple derivative that you need to find. Okay, no chain rule, no implicit differentiation whatsoever, just product or maybe the quotient rule. Okay, so you need to recall back, revise what's the formula for the product and also for the quotient. Okay, number 2, compute xi plus 1. Okay, again, this is the formula that we have derived just now. Okay, when you memorize, just make sure you don't confuse what's on the top, what's on the denominator. And then the stopping condition, perform the iteration until we satisfies any of this condition. Fx equal to 0, okay, the modulus absolute of fxi less than the given epsilon. And also the third one, the difference, okay, the C here meaning the difference between two consecutive x, the current minus the previous x. Okay, because you can see from the graph just now, if your xi, the distance between your xi and xi plus 1 is close enough, meaning that you are already at uh, uh, the root itself. Okay, so that's why we have this condition. So there's no stopping condition for the b minus a like what you have in the bisection, because we don't use the a b term. Okay, but rather x only, xi plus 1 or xi minus 1. Okay, and finally, yes, Jami, please mute your audio. Okay, so finally, of course, you need to write your final answer. Okay, your final answer, your root is taken or is approximated to the latest x that you have. Okay, now look at example 4. I'm going to write manually, but you can refer to your notes since you already have the answer over there. Okay, Syami left dah. Saya suruh dia mute. Alright. Example 3. Okay, example 3 in your notes. Use the Newton-Raphson method to compute the root of blah, 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 blah. Okay, so first of all, okay, be careful when you have this kind of problem. You need to form your own fx first, okay, because it's not stated as a main subject yet. Okay, so fx is 6x exponent of x minus x minus 1. So careful, okay, because sometimes the common mistake is here, this part, okay, because normally students just read in their mind, okay, left hand side minus the right hand side. But when it comes to writing, students tend to write 6x exponent of x minus x still plus 1. Okay, so be careful. There's no harm to write at the first place. Okay, so maybe you want to write at the first place properly with the bracket and so on. Okay, minus x plus 1. Left hand side minus right hand side. Or you can start from the right hand side minus left hand side. Okay, so be careful on that. So it is minus 1 and not plus 1. So that is your fx. And it is stated that your x naught, okay, that you need to use is 0.2. Okay, and then the stopping condition, okay, the difference between two consecutive x must be 0.0005. Okay, so for this calculation that we are going to do, okay, standardized to 4 decimal places, but somehow in the test it will be stated. Okay, okay, manually recall back the formula for the Newton-Raphson xi plus 1 equals xi minus, so at the top we have the fx over f prime. Okay, so first of all, what is our f prime? Okay, so careful, you have the term x exponent of x here, meaning that you need to apply the product. Okay, product rule. Okay, so sometimes this is also mistake also comes from here. Okay, shouldn't rush to do the derivative, but turns out, okay, be the wrong answer. Okay, so it is not the derivative of x, okay, multiply with the derivative of exponent of x, not like that. Okay, so this is the product here. Okay, so do the product differentiation, your f prime is supposed to be, okay, what you have in your notes over there. Okay, so this is actually comes from the product rules. Okay, and then if we put in our expression or the formula for the Newton-Raphson, then it is xi minus, so at the top, so maybe you want to have a proper bracket over there. Okay, then you have 6x exponent of x minus x. So all of the x supposed to be with the subscript I over 6xi exponent of xi plus exponent of xi minus 1. Okay, that is your xi plus 1. So this is the governing formula that you need to do in your calculation, that you need to use in your calculation. Okay, so in your notes, the solution is given in terms of table, but I'm going to show you how to do the manual calculation, how it works. Okay, so always start with the I equal to 0. So I equal to 0, your x naught is what has been given to you, which is 0.2. Okay, so based on the formula, when I equal to 0, at the left hand side you have x1 lah, because I plus 1. Okay, 0 plus 1. So at the left hand side you have x1, but at the right hand side you have x0. All the term on the right hand side, okay, is based on the x0, x0. Okay, so I'm going to put directly the value of x0, okay, at the right hand side, which is 0.2 minus, okay, so you have 6 times 0. Maybe I don't need to use the x. Okay. So 0.2 exponent 0.2 minus 0.2 minus 1 over 6 0.2 times exponent 0.2 plus exponent 0.2 minus 1. Okay, so press your calculator, blah, 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 and so on. You will get 0.1659. This is manual calculation. Okay, and you check the difference between two consecutive x. Okay, this is your stopping condition. So x1 minus x0. Take the absolute value, meaning that you have 0.1659 minus 0.2. So in the table, we have 0.0341. Okay, but if you write on the table, okay, in the table it's already in the second row, I equals 1. Okay, because for the first iteration you already get the x1. All right, so still not satisfies the given condition, so meaning that you need to have I equals 1. Sorry, I equals 1. Okay, so now if you look at the formula again here, the formula here, so when I equals 1, you have x2 at the left, and at the right hand side, the calculation involved with the x1 term. Okay, so what is your x1? Is the previous value from your first iteration. So xi is x1, so you have 0.1659. Minus, so in the bracket you have 6 times 0.1659 times exponent 0.1659 minus 0.1659 minus 1 over blah 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 blah. Okay, so you can see you are repeating, okay, the process. You are repeating the same function but with different values of x. Okay, this is how you do the manual calculation, which somehow I think can be improved, or you can be faster if you utilize your calculator, because you are actually using the same only one equation. Okay, you can just press the calculate button. Okay, so this is but this is how you get the values in your table in the lecture notes. Okay, this is the manual calculation. Okay, so now I'm going to show in the calculator. You can speed up the calculation. Okay, my calculator. Okay, so okay, so you can see only one equation that involved in the calculation of Newton-Raphson here. Okay, so in your calculator, you are going to put, okay, in the calculator, you will store this formula only, x minus 6x exponent of x minus x minus 1 over, okay, 6, then you have a bracket here, x exponent of x plus exponent of x, close the bracket, and then minus 1. Okay, so because in the table, if I can have the table here, so xi. Okay, so always start with a 0, is given to you as 0.2. Okay, now in order to get the x1, okay, the x1 here, you are using this formula, but you put the x value as 0.2, because here this is the position for your left value on your formula. Okay, so the x here is supposed to be 0.2. All of the x should be 0.2. Okay, so in your calculator, first of all, do we have the trigo function? Okay, no, so it's okay. Okay, if you have the degree here. Okay, so I'm going to store the formula now. Okay, so I have alpha x, okay, minus, then have the fraction. Okay, so at the top we have, so I'm going to put the bracket, okay, to be safe, okay, always. So 6 times x times exponent. Okay, so exponent is shift ln, and then exponent of x again, so alpha x minus x, so alpha x minus 1, close the bracket. Okay, so now at the denominator, okay, I have the bracket. Okay, at the denominator, so if you have this kind of calculator, so basically you can just use the derivative term here, d dx here. Okay, but if you don't have this d dx, then you need to put this term here. Okay, 6, the derivative that you have construct earlier, the product differentiation. Okay, but if your calculator have this d dx, so basically you can use shift that. Okay, in that meaning that the calculator will evaluate for you, okay, the product rule, okay, embedded over there implicitly. So in the bracket here, you just put your actual fx. Okay, the derivative will be evaluated by your calculator. Okay, so we put one more time, 6 x shift ln x one more time minus alpha x minus 1. Okay, but your calculator, the derivative, okay, the evaluation of the derivative in the calculator need to have at what point you want to evaluate, at what point. Okay, if you want your calculator to give you the term of the product differentiation, no, your calculator cannot do that. Okay, it just can evaluate the derivative at certain point. Okay, so we need to put the value, okay, x equals to what you want to evaluate, with what value. So in our formula here, okay, the evaluation is at the value of x. So for any x, okay, that you put, okay, in your calculator, then the derivative, okay, will be evaluated at that point as well. So x equals the x lah. Okay, so alpha x one more time. That is what you have. Okay, so you just need to put that formula in the calculator. So if what do I have? Please check. Okay, I don't close the bracket, big bracket over here. Where did I go? I can. Let us try one more time. Okay. Okay, so for first time, it depends. If you already have the value of x, then x is 0.2. Okay. Okay, so now if we use the calculate button, okay, your calculator will ask, okay, what is the value of x that you want to use. Okay, so now you want to fill in your table here for x1. Okay, based on the manual calculation, okay, at the first iteration you have x1 at the left. Okay, how do you get the x1? By using the value of x0, okay, in your formula. So this in the formula you are using x equals 0.2. Okay, so your calculator will gives you 0.1659, exactly what we have computed earlier. So 0.1659. Okay, so maybe you want to have one more column for the xi minus 1. So you can compute the check the stopping condition. So for the first time just now, this is 0.0341. Okay, so you know that you cannot stop yet, so you need to have I equals 2. Okay, and so in your calculator, you are still using the same. Okay, you are using the same formula, but this time when you press the calculate button, you are using the value of x from your previous iteration. So your current x that you need to use is 0.1659. Okay, so this is actually your x2. So 0.1646. Okay, you can check the difference between the current and the previous. So that is 0.0013. Okay, I just take from the notes. Okay, so you cannot stop yet. So meaning that you need to press one more. Okay, press calculate button. But now your x changed to the previous one, 1649. Press equal. Okay, so you have the same one. Okay, when we round off to the 4 decimal, yeah, this is 46, 46. Okay, so of course the difference is 0. So now you're already less than 0.0005. Okay, so basically a student will use the calculate, and after that only then calculate the difference between two consecutive. Okay, because basically if you have like the same x, okay, for the second time, okay, or after two consecutive x, so most likely you're going to stop, okay, at that iteration. Okay, so it is way easier if you can utilize your calculator. Okay, but manually, okay, I've shown you how it works, okay, in the manual calculation. Okay, and finally, of course, you need to write down your final answer. Okay, so therefore, last line, you write your your approximation roots. Okay, it's approximated to the latest x that you have in your table, which is x3, 0.1646. Okay, so that is the Newton-Raphson method. Okay, way easier compared to the bisection. You see, in the bisection, you need to compute FA, FC, C, okay, and then check for the absolute, okay, and so on and so forth. Okay, so easier for the Newton-Raphson method. Okay, any problem? Questions on, sorry, Newton-Raphson? Ada soalan tak? Boleh faham? Alright. Okay, faham Adnan. Alright. Advantages and disadvantages. The advantage first. Okay, with the right choice of initial guess, it converges faster than bracketing methods. Okay, just like what I've explained before. You can see based on the graph. Okay, what did you do in the bisection? Okay, you just cut into two. Okay, at the middle point, but somehow by the Newton-Raphson, by the tangent line, you are actually closer to the actual. Okay, so that's explained why it converges faster, okay, compared to the bisection or any bracketing methods. Okay, easy to convert to multiple dimensions. Is not in our scope anyway, but it can be extended to two dimension. Okay, disadvantage: convergence is not guaranteed. Convergence is not guaranteed. This is okay. Let me explain a bit on that. Convergence is not guaranteed. Okay, so let's say in this graph, okay, so I've mentioned just now, in Newton you only need one initial value. Okay, you need one initial guess. So let's say your initial guess is somewhere here at A. That is your initial guess, and when you do the calculation, it turns out you are moving to the left hand side, meaning that you'll never converge to the x here. But again, it depends on the function that you have. Okay, or your initial guess somewhere here at B, but when you do the calculation, it turns out it moves to your right, meaning that you never reach your roots at the left. Okay, so that uh, can happen. Okay, that can happen in the Newton-Raphson method. So in that case, okay, the convergence, we can say that convergence is not guaranteed. So how we can ensure that we can converge to the solution again is by looking at the initial interval. Okay, so in the test, in the calculation, we want to have, of course, we want to converge to the solution. So at the first place, we have the initial interval, but basically, you don't really need to have it for the Newton-Raphson. Okay, but to ensure that we don't get diverged, so we find the initial interval. Okay, and how do we know that the initial interval is correct? Again, we need to use the IVT to support our justification of why we choose that interval. Okay, so let's say if we have this interval, for example, that is supported by the IVT, then you can choose any value in between to be your initial interval. But in common practice, we can take the left interval, the left limit, or the right limit. Okay, so eventually you will reach, okay, to your roots in the end. Okay, so that's the explanation. Convergence not guaranteed. Division by zero or nearby zero because of the fraction here. Okay, so in some cases, or maybe there are cases where f prime, the evaluation for the f prime is so small. Okay, when you round off to 4 decimal, 6 decimal, okay, your calculator or your program, okay, round off to zero. When you divide by zero, then you have error, invalid, okay, invalid expression. So that could happen as well in the Newton-Raphson method. Okay, division by zero. Must find the derivative. This is with the help of calculator and also computer programming, the must find the derivative here is not more considered as disadvantage. Okay, but if we are talking about manual calculation, then yes. Okay, in some cases, okay, especially when it involves a bit complex term of your fx, then of course the derivative, the f prime, okay, need to be applied with the techniques of derivative. Okay, the suitable techniques of derivative that somehow could be long, okay, or the technique could be complicated to get the derivative. Okay, but again, in terms of a test or exam, we normally give a simple derivative for you to do. Okay, but your calculator can help you with the derivative as well. Okay, so I think no problem on that. Okay, tak ada soalan? Ada soalan on the Newton-Raphson? Okay, faham? If you can get it, then please proceed to exercise 5. Okay, sambil-sambil tu. Do on your own first. Exercise 5, after this, I'll share the Google Sheet so you can put your answer over there. Okay. Buat dulu. Sambil-sambil saya stretch out. Okay, exercise 5. Two tasks here. Exercise 5. Show that there exists a root between 1.5 and 2.5. Okay, the first one. And after that, use the Newton-Raphson to find the roots. Okay, starting with x naught equals 1.8. Okay, buat dulu. In the meantime, if you have questions, you can ask in the chat room or you can simply talk. Sufyan, I don't get your questions. When to use which? What do you mean by that? When to use, oh, you mean when to use the bisection or when to use the Newton-Raphson? Is it? Okay. For you guys, basically depends on the problem. Okay, the problem we stated clearly, use the bisection or use the Newton-Raphson. Okay, but in general, you can choose any methods that you want. But basically, if it is given if it is given the condition, I mean the interval, okay, you can always start with the bisection, okay. X1 lies with, okay, I'm going to share the Google Doc first. Okay, put your answer in the spreadsheet. Yeah, I've put the link in the chat. Exercise 5. Try to use 4 decimal in your calculations, standardize to 4 decimal places. All right. Okay. So 1.9446. Right. So this is the correct answer. Okay, so the root is 1.9446. Okay, um, but on top of that, you should prove the existence of the root first. Okay, so basically you compute the f 1.5 and then f 2.5 and see that the multiplication of fa and fb, okay, f 1.5 times f 2.5 is actually negative. Okay, and that proves the existence of the root in 1.5 and 2.5, interval 1.5 2.5. Okay, so that is Newton Raphson. Any problem?